So now we're going to move on to the role of public health in climate adaptation and mitigation planning. And for that segment, we will hear from Patrick Kinney, who is the professor of environmental health sciences at the Mailman School of Public Health and Earth Institute at Columbia University. He directs the Columbia Climate and Health Program and has a broad background in air pollution and health with specific expertise in exposure assessment, health effects, and interactions with climate change. And with that, I'd like to ask Professor Kinney to come up.
Thanks very much, and thanks for inviting me to join the symposium today. I want to talk about public health. I think public health can play a role or should play a role in sort of planning around climate change, both mitigation and adaptation. And, you know, as we've seen in other environmental issues like air pollution and water pollution control in the past, although there are many reasons why it's good to have clean air and clean water, public health benefits end up often being the driving force for policy action and sort of continued motivation for that policy. So I think public health always you know, has played an important role in environmental policies, and I think it hasn't gotten so involved in the climate planning process so far, but I think it's starting to, and I wanted to illustrate with a couple of examples ways that I think it can play a role. As was mentioned, my own background is mostly on air pollution and also heat and temperature in general. So the examples I'm going to talk about are you know, in those fields from my own research. But I think there's hopefully general applicability of some of the issues I'm raising to the broader set of issues on climate impacts like coastal storms and things like that. So I'm going to start off by just, you know, this is very simple kind of definitions that, you know, we kind of have, you know, if you want to distill it down to very simple terms, we have kind of two levers for dealing with climate change. We can certainly we need to mitigate as the last talk was illustrated quite nicely. There's many initiatives at the local scale, regional scales to do that here and abroad. But also, you know, meanwhile, climate's been changing due to human influences for the past 30 or 40 years, and you know, we need to adapt, and it's going to continue to get, it's going to change a lot in the next 30 or 40 years, no matter what we do on the mitigation side. So we have to be kind of working on both in parallel, and I think both are extremely important. So here's how I think public health science can play a role. So on the mitigation side, we can look at public health aspects of mitigation. You know, we have many different ways, as again nicely illustrated by the last two talks. We have many different ways of mitigating climate change or greenhouse gas emissions, really. And some of those bring coincident health benefits, and some of them don't, and to a greater or lesser extent. So by looking at the public health aspects of mitigation actions, we can try to help to prioritize, I think, which actions on the mitigation side might be most healthful. And then secondly, we can use public health science to identify and prioritize adaptation actions by sort of pointing out what's coming down the pike in terms of risks related to, you know, extreme heat or extreme storms and that sort of thing, by doing assessments and forward-looking assessments to try to anticipate what's happening. So I'm going to give an example of each from my own recent research and then hopefully draw some broad conclusions from that. So the first one is a co-benefits analysis looking at sort of how mitigating different kinds of emission sectors could have greater or lesser benefits for public health. This particular analysis we did was done on a global basis, so it's very coarse scale, kind of broad brush, but the same kind of analysis can be done on a much finer geographic scale, you know, in a city or a region or a country. And in fact, the same basic analysis has been done if you look at the justifications for the new EPA CO2 rules, going into the EPA regulatory impact assessment that was done in preparation for that. They did a lot of the same kind of analysis, looking at the health benefits that come from the actions to reduce CO2 emissions, sort of the coincident health benefits. So what I looked at in this analysis was looking at the question of how mitigating emissions from different kinds of sectors around on a global basis can both reduce greenhouse warming and at the same time reduce cardiovascular deaths related to fine particle pollution. So just to get into some of the methods very briefly without too much detail, there was a model that was run on a global basis from the Goddard Institute for Space Studies. Nadine Unger, who's a collaborator from formerly of GISS and now at Yale, did the modeling work. And what she did in this analysis that I'm talking about here is looking at global warming potential by 2020 based on emissions from these different sectors. What she found in the global warming part of the analysis was that, not surprisingly, that by 2020, warming was mainly driven by short-lived pollution species like black carbon and ozone, which also have important health effects. And that in her analysis, road transport emissions, building-related heating emissions, and power generation were some of the important source categories that had the greatest warming potential. I'll show you some data on that in a second. So this work began looking at the warming part of the analysis, but Nadine Unger's global model also examined particle concentrations because that was part of the pollution mix that was examined. And so we thought it would be interesting to take those particle data and look at the health impacts of those different emission sectors. So the concentrations of PM2.5, which is the sort of best simple metric we have of health-relevant air pollution, was estimated in the standard units of micrograms per cubic meter, summing up the components some of the key components that make up fine particles, sulfate, nitrate, black carbon, and organic carbon aerosols. And we computed annual average concentrations on a grid around the globe, and then linked that to population data to try to estimate health impacts. This is a map showing the grid of PM2.5 concentrations. This is summing up the contributions of 13 different emission sectors, which we'll see in a moment what those different emission sectors are. And this isn't meant to, you're not supposed to necessarily read all the details, but just to give an idea what the global picture looks like of, at least at a very coarse scale. This is a 4 by 5 degree grid, so these are pretty coarse, pretty big boxes that are being modeled, but we are able to do it on a global basis by having that fairly coarse grid. The health impact assessment followed a fairly standard methodology, but maybe it's worth running through quickly because you're probably not necessarily all familiar with this. So the idea is you first look at historical health effect studies, epidemiologic studies, and that's what the first bullet refers to is we understand quite well the quantitative relationship between different levels of PM2.5 concentrations and different levels of cardiovascular mortality. And that's based on the American Cancer Society cohort study that was a US-based study that's widely used in these kinds of analyses. So that gives us a functional relationship between a percent change in mortality for a 1 unit change in PM2.5 concentration. We had to get baseline cardiovascular mortality rates around the world from the World Health Organization in order to compute changes in those rates. And so then we combined that with the health impact function to come up, and also the PM2.5 concentrations to come up with estimates of the mortality. So on the next slide, I'm going to show you a graph that has cardiovascular mortality on the y-axis and warming potential based on temperature, degrees Celsius temperature change on the x-axis. And each of those dots is a different emission sector from this global modeling effort. And you see that there's a dotted line in the middle that is the 0 line in terms of temperature change. And so there are some sectors which by 2020, the emissions are actually cooling, having a cooling influence. That may be surprising to many of you, but the reason is that some of the emissions from these sectors include sulfate particles, which reflect light back to space and actually result in cooling. And also some of the organic carbon particles also are good at reflecting light, or at least are have a cooling influence. And so some of the sectors actually by 2020 are cooling the planet. But there's a whole bunch of other sectors which warm the planet, and road vehicle emissions stands out especially, but many others as well, and household biofuel burning up here. But you see cardiovascular mortality burdens differ quite a lot from one sector to another. And we can use this kind of analysis to identify emission sources or sectors that are in this upper right-hand quadrant that have both high mortality and also high warming potential. And household biofuel burning would sort of, based on this analysis, would seem to stick out as well as road vehicles. There's none that are really way up in the right-hand corner, but at least, if we try to go after mitigating these emissions, we're going to get cardiovascular mortality benefits on a global basis. So that's the basic argument. So based on that, this first case study, we concluded that a couple of important sectors seem to have influences on both health and climate in the near term. Other emission sectors actually contribute significantly to warming, to the health burden from fine particle pollution, tend to have net cooling influences on the climate in the near term. And so near-term policies might want to focus on emission sectors that have the greatest health benefits. Now, if you look at the longer term, which this analysis also did, and I don't have time to show you, the picture changes a little bit. So some of those sectors that, like the power sector, which in the short term is producing a lot of sulfates and cooling the atmosphere, in the long run, the CO2 emissions end up dominating, and because CO2 stays in the atmosphere for a long time. So you need to look at both sort of a short and a long-term perspective. I'm just showing this as a sort of an illustration of how this analysis can be done. So I'm going to now move quickly to the second point, which is to how we can use public health science to identify and prioritize adaptation actions. So the idea here is to examine the future potential health impacts and try to think about which health impacts we need to adapt to and get ready for. So we're going to study the historical exposure response relationship for temperature and mortality. In this case, I'm looking at temperature, and then look at future scenarios of impacts at the local scale in New York City. This is based on a paper that we published in 2013 that's listed here in Nature Climate Change. What I'm going to start off by showing you is this graph, which is the graph of the relationship between daily death counts and daily temperatures in New York City over like an 18-year period. I think it was 18 years, it probably said on that last slide. 1982 to 1999 is the time period that we had data for. So what we did was a regression analysis using observed data from the past, looking at the relationship between daily temperatures and daily deaths. And we see that, as is very commonly seen in cities around the world, there's a kind of a U-shaped relationship. So at colder temperatures, we see an increase in mortality risk. And at higher temperatures, you see sort of an upward sloping increase in mortality risk. And so you can imagine, so this is what's been seen historically in New York City. There's kind of like there's a healthy range where temperatures don't have too much of an impact. You can imagine that as temperatures shift to the right, the distribution of observed temperatures shift to the right, we could end up being more, shifting more to this end of the distribution and potentially facing more mortality related to temperature. So we also, so we did this historical analysis. Then we worked with some climate scientists at the Goddard Institute for Space Studies, I'm sorry, I should just say GISS, which is based in New York City, right near the Columbia campus. And Radley Horton, who's the GISS scientist that we worked with, was able to download 32 different future temperature projections from 16 climate models and 2 IPCC emission scenarios based on the IPCC fourth assessment report analysis. So this work was done a couple of years ago before the latest IPCC report just came out. And then we downscaled those temperature projections for the future to the Central Park Station for the 2020s, the 2050s, and the 2080s. And we compared those to a baseline period that was from 1970 to 1999. So the idea is we're going to look at the impacts of these future temperatures based on our understanding of the mortality impact of temperatures in the future. And so the next slide shows some of the results. I know it's kind of small, but what we have here on these graphs is the different decadal periods, the 1980s, the 2020s, the 2050s, and the 2080s. And the bar charts, or the box plots in these each of these little sections show the results in red for the A2 scenario, which is a higher emission scenario, and the B1 scenario, which is a lower emission scenario. And then what you're seeing plotted on the y-axis is additional temperature-related deaths in those decades compared to the baseline period, yeah, in comparison to what the number of temperature-related deaths were in the baseline period, which is over here. And so you see that what we did, we separated out the heat effect from the cold effect. You actually get a benefit due to the warming in the future in the wintertime, so that wintertime mortality impact diminishes somewhat. You get an increase in the summertime high temperature effect. And if you add these two together, what's plotted at the top is what we call the net effect. So based on our analysis, it seems like the benefits in the wintertime don't outweigh the worsening in the summertime. So based on our analysis, we see a gradual increase in the mortality due to temperature warming in the future. Although the results vary a lot depending on what the future looks like. If you end up with a very high emission scenario on a global basis, then the impact could be much greater versus a lower emission scenario. And also note that by 2050, 2020s and 2050s, the two scenarios don't look all that different. It's really the end of the century when they start to really deviate. So that's where the mitigation that we're doing now can really have a benefit, is down the road by the 2080s. We don't see so much benefit in the near term from the various different kinds of emission pathways. So this kind of analysis, I think, can be helpful for planning for sort of resilience and adaptation needs on a urban scale. And so based on this analysis, just some quick conclusions. We associated daily mortality with both cold and warm temperatures in an 18-year data set from Manhattan. And then we projected future mortality impacts of changing temperatures based on a range of emission scenarios and also different climate models. And we saw some small decreases in cold-related deaths and bigger increases in heat-related deaths, which yielded a steady increase in the net annual heat-related or temperature-related mortality across decades. And the higher, not surprisingly, the high greenhouse gas scenario by the end of the century was having much larger impacts on mortality. There's some very simple aspects of this analysis. We held population constant. We didn't allow that to grow in the future. We assumed the exposure response function stayed the same, which is probably not true. It seems like actually populations are adapting already to heat-related mortality because of increasing air conditioning usage over the last couple of decades. So actually what we need to do is think about diminishing the exposure response probably in these analyses. Also, we assume that baseline death rates would be the same in the future, sort of the foundational impact of mortality. And actually, the current work we're doing now I have a new student who just finished her work a few months ago, and she's now started to relax some of these constraints and start to model future patterns of adaptation and population change, and seeing how that changes the analysis. So overall summary for the talk, just wanted to point out that I didn't really show you information on this, but you probably saw it on the first day of the symposium, that global warming has been accelerating and certainly going to continue for several more decades regardless of current actions. So we need to adapt. We need to deal with what's happening. We also need to be mitigating as aggressively as we can. I think public health science can play a role in both of these kinds of plannings, both mitigation and adaptation, and I tried to illustrate that from a couple of examples. These are just meant, again, as examples for how we can sort of bring public health into the assessment process. We have a lot of information about health impacts of different kinds of climate extremes and also related air pollution in the mitigation side. So it's just a matter of doing the analyses to see how public health changes in relation to various kinds of actions, both on the mitigation and adaptation side. There's a lot of people that have been involved in all this research, and I just list them here. I won't go through them in detail. Some students, some colleagues, other faculty and postdocs that have helped me with all this work. And then I think this is my last slide. So I think there might be time for a question or two.
I think not. Why don't
No?
we wait?
Okay. Okay.